Alright, cool. We are good to go. Alright, so, questions? Alright, no questions. I will take that as a good sign. So we talked about recursive algorithms yesterday, and we looked at a recursive view of tree traversal in 3 different orders: in order, pre-order, post-order, and saw a 4-line algorithm for printing the contents of a tree. And then we looked at insertion and searching, and those were also recursive and fairly succinct. And we ended by starting to talk about deletion. And so let's dig further into the deletion algorithm. So our setup is, we've got some kind of tree. And we want to delete a number from it. And, if we want to delete the 10, for example, so get rid of this, the difficult part is that 10 has children. It's got a 5 and a 15, and, this could have more children of its own, and the 15 could have, children. And if we just get rid of this node, we've got, 2 subtrees with nothing pointing to it. And so something needs to adopt this subtree and that subtree. Since we're getting rid of 10, its parent, has an open spot for 1 child, but not for 2. So we need some way to restructure all of this so that it's all connected, and it still acts like a binary search tree, but that 10 has been removed. And it turns out we can do this recursively and solve most of our work without actually doing anything. So here's a recursive delete function. So this is just like insert. It's going to have to return a pointer to a root. So delete the node with this number from the tree with that root. CAPTCHAs. Do you have to do CAPTCHAs to get into Zoom? I don't like CAPTCHAs. I guess they're cool though. All right, so we want to delete the number from that root. So here's the easier part of the algorithm. So if our number is less than the root, let's just use our delete function to delete our number from the left subtree. If this was the root of the tree, 20, and we wanted to delete a 10, we know that 10 is smaller than 20, so it's somewhere in this left subtree. So let's delete 10 from that subtree. And then the result of this will be a tree that looks like, the old tree, but is missing the 10. And let's make that the new left subtree of the root. And then let's just return the root of the tree. Some of those CAPTCHAs are beyond my capability. It's like, identify which of these are foods, and there's like things on there I've never seen that, I guess could be food, but, could also be like something you stumble across in the woods. So, I don't know. If you don't get out enough like me, sometimes those are challenging. I had a friend who worked for the Forest Service, and he said they had a problem with bear-proof garbage cans, because there was an overlap between, as far as opening these garbage cans, between the smartest bears and the most challenged humans. And if they came up with a design that no bear could open, there were also people who couldn't open it. And if they came up with a design that every person would be guaranteed to be able to figure it out, there would be some bears that could figure it out also. And so that's the bear-proof garbage can syndrome. Alright, so if our number is smaller than the root, delete the number from the left subtree, make that the new left subtree, and return the original root. Same thing on the other side. If our number is bigger than the root, then set the new right subtree to be what you get when you call your delete function on the right subtree to delete that number and return the root. Can bears perform binary searches? I don't know. It's a good question. Yeah, I actually had a hard time with one of those bear-proof garbage cans at Yosemite. Alright, so this is recursive so far. If we want to delete something smaller than the root, something bigger than the root. The challenge is when we want to delete the root. And this is in some sense, you know, the worst possible scenario, because the root of the tree, if we just get rid of that, everything in our tree has been abandoned, right? Everything is a descendant of the root. So certainly if we're going to get rid of this node, we've got to do something to patch up, you know, our tree so that we still have access to all of this stuff and all of that stuff. And the root of our tree is going to change because the root was a 20. So the root's definitely going to be different afterwards. So we need a way to delete the root. And this is the one thing that's not going to be a recursive algorithm. This is one of those rare cases now where we have to actually do some work. Everything else we're just, you know, deferring to our future selves in a process called recursion. So how can we delete the root of a tree? Yada, yada, yada. Alright, so, let's suppose we want to delete the root of this tree. So we want to delete the 20. So we're going to use the following algorithm, and we'll add special cases to this as we go. But here's the basic approach. 2 steps. 1, find the largest node in the left subtree. And 2, make that the new root. So find the largest node in the left subtree and make that the new root. So what would that do in this case if we're deleting the 20? Come into the left subtree, that's all of this stuff. Find the largest node, that's a 17. We're going to make 17 the root. So the world would be better if we could block users from deleting the root, except if you look at our recursive algorithm, that's the only thing we ever delete. Even if we're deleting something that's not the root, we're going to keep recursively making calls to delete until we get to the point where we're calling this with a tree whose root we want to delete. So this case is always going to come up. Even if we're deleting the 5, eventually we'll call delete with this tree and say, oh, delete the root. which is kind of a little freaky. All right, so basic two-step algorithm. Find the largest node in the left subtree, make that the new root. We could also do the smallest of the right, but we're absolutely not going to do that for PA4. We're going to do smallest from the left. But everything that we're going to describe, we can do exactly the same thing in a mirror kind of way, smallest node on the right. So yeah, left is arbitrary. All right, so why does using the largest node in the left make sense? Two things. One, we're going to make this the new root. If this is still going to be a binary search tree, it has to have the property that everything to the left of the root is smaller, everything to the right of the root is larger. Well, since this is coming from the left subtree, we already know everything that was to the right of the original root is going to be bigger than this, because this was in the left subtree of the root. But if we move this up here, since this is the largest node in this subtree, everything else in this subtree has got to be smaller than it. So when we put 17 up here, all this stuff will be smaller than the new root. It will still be a binary search tree. And we're not changing the order of anything inside here or anything inside here. So you could formalize that into a proof that this is still a BST after we move the largest node from the left up to the root. The other thing that's nice about this is that 17 is guaranteed not to have a right child. Why? Because if there was a right child, it would be larger than 17 by the fact that this is a BST. So 17's right child is null, so when we move it up here, it can adopt the old right child of the old root. So that works well, but there's one other issue here. Everybody good so far with this particular tree? Why moving 17 to the root makes sense? Good, good. Okay. So there's one other issue here. So the way I drew this, 17 had nothing to its left, which means it was easy to make all of this old left subtree the new left child of 17. But that's not always the case. So let's complicate this a little. And we're just going to keep adding more and more complications today. So let's suppose that 17 had, I don't know, a 15 and a 16 like that. So 17 already has some stuff on the left. Well, if we move 17 up here and we make 17's left child this whole subtree, now this little subtree on the left of 17 has been orphaned. So before we move this up to be the root, we can say have, let me call this largest node n. We can have n's parent adopt n's left subtree. So this little subtree, 15, 16, this is going to get adopted by 14 on the right. And so let me make a little less ridiculous looking example. So there's stuff going on in there, and we're deleting the 20. So we're going to take the 17, move it up to be the new root, so this will be 17. This will be the whole subtree that was on the right with 40 and everything else going on. the left child of the root will be the same as what it was. But then 17's parent, 14, is going to adopt this little subtree that was on the right. So that's what our deletion will result in. All right, so let's start breaking into cases. How do we find the largest node in the left subtree? And this is ODP 215, which is Monday's ODP, due Tuesday. So how do we find the largest node in the left subtree? Well, we've got the root. Let's go down to its left subchild, right? That's a subtree. And if we start at the root of that and we just keep moving to the right as far as possible, when we get to a node that has no right child, that's the largest node. Right? We know that's the largest node because if we move to the left, we're going to get to something that's smaller. And if there is something larger than 10, it's got to be on the right. And if it's larger than 14, it's got to be on the right. And if it's larger than 17, it's got to be on the right. Well, there's nothing to the right of 17. That must be the largest node in the left subtree. So how do you do this? Start from the root, move to the left, and now go into a loop where you start moving to the right as far as possible. And there's a few edge cases here. So let's delete from some tree, some number. And again, I'm just assuming that our number is in the tree, okay? That I'm assuming that you know, we're not deleting a number that doesn't actually isn't actually found in the tree. In which case we know t is not null, right? So the first edge case, if t left is null, then we can't do what we're describing. If there's no left subtree, we can't find the largest number in the left subtree. All right? But in that case, we have a really simple way to delete. If there's nothing to the left of 20 and we want to delete 20, just change the root to be 20's right child. So if t left is null, just return t right as the new root. You got to free memory every time you delete. I'm not going to put that in here. But yeah, you have to free the memory somehow. Okay, so that's one edge case. But the more typical case, there is something to the left, so we need to find the largest node. And yeah, if there was no 17 here, then this would be the largest node. Cool. Welcome. All right. So, you know, left subtree equals t left. All right. So now we're just looking at something like this. And we're going to do basically what we did with linked lists. We're just going to march down this linear collection of nodes, just moving to the right child until we get to the end. And our goal is to find, you know, the largest node, but also to remember who its parent was. So we're going to use this previous current business that we used in linked lists. We're going to start off with this 10. And assuming it has something on the right, we'll make this current and this previous. Assuming there's something to the right of that, we'll move current to here and previous to here. And we'll keep doing that until there's nothing to the right of current. And at that point, we've got two pieces of information. This is the parent of the largest node, and this is the largest node. And there's another edge case here, which is if our tree looks like this, right, and maybe there's, you know, stuff going off here, but if the largest node in this tree is the root itself, then we can't, you know, march down here with this parent previous business and so on. So that's our final edge case, which looks something like this. So we're trying to delete the 20. We want to find the largest node in the left subtree. Well, in this case, the largest node is sitting right there at the root. We start from the root, but there's nowhere we can move to the right. We can't even move down one spot. And in that case, what should this tree turn into? Well, the largest node is the 10. That should become the root. Everything on the right should stay the same. And the left subtree of that node does not change at all. So there's your tree with 20 deleted. All right, so you got to think about a few edge cases, but let's do the general algorithm for deleting this. And we're going to use lots of temporary variables here. And the code will be simple once we have temporary variables pointing to all of the nodes that we care about. So I'm going to use t for the root of the tree, right? So that's the root. And I'm going to suppose that I've, you know, moved to the left and started moving down to the right and gone as far as I can until I get to a point where I have my largest node, which I'm calling C for current. And I have the parent of C, which I call P for previous or parent. And now I want to delete that 20. And the code kind of writes itself. Okay, so C is going to become the new root. C does not have anything on the right. If it did, it wouldn't be the largest thing in this tree. So C's right child is currently null, so we can change C right to adopt everything to the right of the node we're deleting. So set C right equal to T right. And then C left, since C is going to be the new root, has to adopt everything to the left of the original root. So C left equals T left. And remember, C might have something to the left to begin with. And if we change C left to pick up all of this, this stuff gets orphaned. So before we set C left to the left of the original tree, we need to take care of C's current left child. And the parent is going to lose its right child, which is C. So in place of that, it's going to adopt C's left child. So P right is going to take C left. And then we're completely done with T now. We've passed off both of its children to the new root C, so we can free T. And we need to return the root of the new tree, and the new root is C. So other than all the code for dealing with edge cases and the code for moving down here, jumping to the right, keeping track of previous and current, and finding P and C, once you've done all of that, it's a few lines of code to actually do the deletion. And once again, this code, I don't want you to fall in love with it. Okay? I don't want you to type this into your program and then try to figure out what it does. What would work better is to think about the algorithm for deleting the root of a tree. Go through this in whatever way works for you. Paper, whiteboard, stories, whatever, colors. And really work with this idea of finding the largest thing in the left subtree, moving that to the root, adopting that thing's left child to the parent on its right, and so on and so forth. Figure that out. Figure out those steps. Understand the algorithm. Forget about this, right? Think about the manipulation of memory. That's what your task is. And once you understand what you want your program to do, now write the C code to do it. And if you're using temporary variables to point to all the action points, this should just kind of fall into place. Right? I want the node C to be the new root of the tree. Okay, so it's got to have this on the right and this on the left. Well, that's that statement and that statement. And I want its parent P to adopt its left child on the right. Well, that's that statement. Right? So I keep saying this, and this is even more true in this case than it was with linked lists. Try to understand what's going on at this level. And then this comes from that understanding. Right? I don't know anybody who, when they want to manipulate a tree, thinks of it in this term. Right? They think of it in these terms, and then they write C code to tell the computer what it should do to match what they want to happen with the memory. So yeah, keep this in your notes and you can refer back to it, but your goal is to get here from this. And I've said, you should leave deletion for last in PA4, but you can write yourself, practice code doing binary trees on integers. And we did that, in the beginning last week. When we started talking about trees, we inserted integers, we printed integers the other day, and so on. Play around with binary trees of integers. Don't try to figure out deletion directly inside PA4 because you're dealing with nodes with 3 different fields. You have to dynamically allocate space. There's all kinds of segfault potential. You got to add 1 to the string length, all of that stuff. Forget all of that, right? Fight one battle at a time. Work on PA4, get your pieces working that you want. When you're ready to switch gears and say, I want to think about deletion for a while now, right? Push PA4 aside, go into a different directory, write some code for doing binary trees on integers, make an insert, make a traverse, and so on, and then start playing around with delete. And build up to it, right? First, make something that will take a tree and tell you what the largest thing is in the left subtree. That's ODP 215, by the way. And make something so that while you're doing that, you can also figure out what node is its parent. Or know if there is no parent because the very first thing, the root of the left subtree, is the largest. And then go ahead and deal with these cases. And then go ahead and deal with the edge case where there is nothing to the left of the root, in which case we simply change the root to root arrow right. And then once all of that is working, go back to the full recursive version, which recursively calls delete until you get down to the spot in the tree where the thing you're deleting is the root, and then at that point tie in all of your delete code. So delete is a big function, right? It's a complex routine with lots of special cases and lots of sub-functions sitting inside, the third of 3 conditions, 2 of which are handled recursively. So that takes some doing. It's really wonderful once you get it working, though. It's like super fun to play with, and delete nodes and print them out, and delete nodes and print them out, and delete the last node in your tree and see that your tree nicely turns back into null with no seg faults or memory issues. That's a glorious feeling. So build up to it, right? Don't just try to do that in PA4 because that's complexities on top of. What are the test cases that will cover everything we could think of for delete on PA4? So deleting the last node in a tree is certainly an edge case. Deleting the root when there's nothing on the left. Deleting the root when there's nothing on the right. And yeah, I would just you know, deleting the root of that tree is certainly an edge case. Deleting the root of that tree, deleting the root of that tree. Those are all probably separate cases. And I would just try, you know, a few of the basic shapes. And again, you're welcome to pass around executable code, right? Don't compile with -G, but if you want to share executable code and say, hey, can you break this for me, right? That's a good way to do some testing and try to break your friend's code. And if you do this for, you know, a tree of integers, it's a whole lot quicker to do your testing than it is for doing license plates and names and stuff. Yes, crush your friends' hopes and dreams. No, don't. But break their code at least. Is there any way to automatically test what? Not in general. It really depends on the code and what it's supposed to do. Automated code testing is an interesting area, though. And it's a challenging area. I mean, so we run into this problem in circuit design, right? You look at a modern processor, it has a few billion transistors inside. How do you know that that processor is doing the right thing? And, you know, sometimes a company like Intel releases a new version of a processor, and there are bugs in it, right? There was the famous divide bug in the Pentium processor not that long ago. And so you know, you try to come up with things that exercise a system in a sufficiently rich set of ways to be able to say, you know, we're X% sure that this is working correctly. But that's really hard to do. So if you do a course in software engineering, I think you'll get into some of that. And you know, sometimes while you're writing something, you can be thinking of how would I test this. But in general, it's a really hard thing. And I don't know how I test code. I have a knack. I'm pretty sure I inherited it from my dad. My dad was a system quality engineer at IBM. And he had a knack for finding problems. And so I seem to be able to do this with code. Hold on one second. Thank you so much. So I'll start testing code, and sometimes I'll just get a feeling, and it's like, well, let's try putting these things in the opposite order and then deleting the first. And bang, a seg fault comes out. Let's see. I heard at a conference a security expert was able to set a printer on fire by hacking. Interesting. Yeah, so yeah, it's a cool area. You know, you can probably smoke your CPU by hacking because the clocking inside your CPU is controlled by software. There's registers you can change to control, you know, how quickly the memory clock is, or the CPU clock, or things like that. Certainly things like fan speed can be controlled, so could you actually smoke somebody's CPU by overclocking it and shutting off the fans? Yeah, I think probably you could. Printer, I'm not sure how much is adjustable inside a printer, so I doubt that there's a way to crank up the intensity of the laser for a laser printer. But, you know, if it was like an old dot matrix, can you drive the motors at a speed that would cause them to overheat? Maybe. I tried overdriving a printer, a hard drive, an old large-scale hard drive, by moving the read-write head back and forth at different rates to try to hit the resonant frequency of the spinning platter, and got as far as where it made a big clunk and shut itself down, and then I kind of freaked out, so I stopped experimenting with that. But yeah, there's a lot of stuff that that we can do in software that interacts with hardware in potentially strange ways. Yeah, and Stuxnet, that was going after centrifuges, same idea. It's kind of scary, you know, and we're seeing this with self-driving cars, right? So malware or, you know, simple buggy code that takes out your braking system, takes out your steering, things like that. It's good stuff to be aware of, and usually people who study computer science, people who work as programmers, are some of the ones who trust technology the least, and there's a reason for that. And yeah, high demand for penetration testers in the future, definitely. All right, so that's tree deletion, and like I say, play around with integers, and build it up in steps for sure. Do not write your entire deletion function and then start trying to test it, right? That's a whole lot of work. Build it up in steps, and get each piece working along the way. Oh yeah, yeah. You always see band-aids over people's cameras. All right, let's Alexa, yeah. It's an interesting question. I do not trust Google, but I know the ways in which I suspect they're not trustworthy, and I'm okay with it. So I believe that, you know, most of these things that I interact with online record my search habits and my keywords and, you know, everything that I'm doing, and I'm okay with that. And I believe that that's available for sale to the highest bidder, or even not the highest bidder. And, you know, I've accepted that. I think the danger is if you don't realize, you know, what's going on. If you think that nobody is recording every single thing that you do and keeping it forever, then that's potentially dangerous. Is there a way to figure out if there's something on a bit byte level transmitting over the net that we don't want, like at a hardware level? That's really hard to do too. So yeah, you can do things like Wireshark to actually look at packets, but then there's things like covert channels where you modulate, say, the length of the packet, and you code information in that length itself. Stuff like that, right? How do you know what coding technique is being used to send something? Don't use the internet, right? Don't talk out loud, because if you talk in your room, the windows vibrate. And if you go across the street and bounce a laser off the windows, you can pick up the modulation of the window pane and reverse engineer that into the sound in the room. I mean, you know, everything affects everything, and so there's almost no way to actually do something in isolation. And that's good or bad depending on your perspective. All right, so let's this is like stuff I would love to just like talk about for a bunch of classes, because I think it's really interesting. And if you do a course like in cybersecurity at a university or crypto, you'll get into all this kind of stuff with people who know a lot more about it than I do, and I think it's a really cool area. So let's take a look at tree insertion. And so I have these itty bitty teeny weeny yellow polka dot worksheets that I've made to simulate what happens when we call our insert function recursively. And so let's just play around with this for an example, just to kind of wrap up our week. Let's suppose that we have a tree which looks like this. All right, so 20, 10, 12, 5, 30. And we want to insert, I don't know, let's insert the number 11. And I'm going to set root equal to the return value from calling this insert function. And I want to see what happens when we call insert. So I've made a little tiny copy of the insert function here. And what we're going to do is we're going to track how insert happens. We've got about 6 minutes to do this. So from main, we're going to call this insert function. So I'm going to label this page 1. This is the thing that was actually called. And we're saying insert the number 11. And the root that we're passing is this little tree up here. So let me draw a picture of that. It's a 20, it's a 30, a 10, a 5, and a 12. All right, so let's start executing the insert code. The first thing it's going to do is say, is root equal to null? And it's not. Root is pointing to a 20, so none of this code happens. The next thing it's going to say is our number bigger than root data? Well, our number is 11, root data is 20, so our number is not bigger than root data, so none of this stuff happens. So now it's going to execute this statement, which says call the insert function. And it's going to call it with root arrow left, that's this little tree, 10, 5, 12, and with a second argument of number, which is still 11. So this call is in progress. And since we're calling insert, all of this information is going to get saved. It's going to get pushed on the stack. So I'm going to push that off onto my stack, which is over here on the side of my desk. And I'm going to start a new call frame. This was called from page 1. The first argument was this little tree, 10, 5, 12. Right, that was the left subtree of our original root. Our number is 11, that's the second argument, and now let's execute the insert function. So if root equals null, well, root is not null, so none of this happens. If our number is bigger than root data, well, our number is 11, root data is 10, so we're going to execute this code. And the first thing we're going to do is we're going to call our insert function. 2 arguments. First argument is going to be root right, that's a 12. Second argument is going to be num, that's 11. So we're going to start executing this. We're going to make a new call frame. This is going to get saved on my stack. My root, my number, my temporary variable, all of that. So I'm going to make a new instance of this function. So I'm going to call this page 3. It's called from page 2. The number that we're passing is 11. The root was, the right subtree of this thing's root, so the root just looks like 12. And we're going to execute our insert function. So if root equals null, well, root is 12, so none of that happens. If our number is bigger than root data, well, number is 11, root data is 12, so none of this happens. So it's going to say, let's make a call to the insert function. Let's insert our number into root arrow left. Root arrow left is null, number is 11, so we're going to call insert with null, comma 11. So we start making a call to insert. This goes onto the stack. And we start our 4th call frame, called from frame 3, number is 11, root is null. And we get into the insert function. First thing it says, if root equals null, and guess what, it does. So we're going to set temp equal to malloc, so we're going to get a chunk of memory. We're going to set the data equal to num, which is 11. We're going to set the left and right children to null, which I'm not going to show. And then we're going to return this node, temp. Where do we return to? We return to call frame 3. So we pop that off the stack. And we're just finished this call to insert. And this statement says set temp equal to what insert returns. Well, what did insert return? It returned temp, which was an 11. So up here, when we say temp equals insert, temp's going to look like 11. And now we're done with that statement. And now we say root left equals temp. So we put an 11 down here. And now we're going to return root, which is this. Where do we return? Where we were called from. We were called from frame 2. So let's go back to frame 2. And we were in the process of executing this call to insert. We just returned, and we returned this tree. And this statement says set temp equal to the return value from insert. So temp is equal to this little tree, 1211. And now we're done with that statement. And now we say root right equals temp. So here's root. We're saying take its right child and set it equal to temp. So that's a 12 with an 11. And that finishes that, and now we say return root. So the return from this call to insert is going to be this tree. We were called from page 1, so we go back to page 1. We were executing this call to insert. We just came back, and the return from insert was this, a 5, 10, 11, 12. And the statement says set temp equal to that. So temp is going to be equal to 10, 5, 12, 11. And we're done with that statement. Now we say root left equals temp. Here's the root. Its left child should now be this tree. So 10, 5, 12, 11. And we've done that. And finally, we're going to return root. So this call to insert is going to return this tree. Where was this called from? This was called from main. So let's go back to main. Main said root equals insert. Well, we just called the insert function. And the return from that was this little tree right here, and this says set root equal to that. So now root's going to be equal to a tree containing 20, 10, 5, 30, 12, 11. That's the tree that results. So that's a really kind of gory view of what happens when we make this one statement. This is a single call to insert, but all of these different call frames transpire and work together so that when we come back from this call, our root looks like that. We don't make mistakes, just happy little accidents, exactly. So again, we don't always want to think about this level of recursion. We usually want to be thinking of it from a higher level, but it's instructive sometimes to try to go down to this level and actually see what's going on in these recursive calls. So that's something you can think about. All right, we are out of time. I will see you in 2:15 if you're there. If not, I will see you next week. Have a fantastic weekend. Take care.